In this video, we're going to talk about the use of some derivatives in solving some physics problems. So I'm going to use my example of my car again on the ground, and it's going to be traveling at a certain velocity. But the velocity, let's see, the velocity is going to be a cubic. It's going to be the velocity as a function of time is going to be 2t cubed meters per second. Okay, and what we're going to try to find is the acceleration exactly at 2 seconds. What's its acceleration rate at 2 seconds? So when we're doing these derivative type problems, we're also going to draw a couple of graphs. So this is, since this is motion kinematics, we're going to draw our three graphs here: position versus time, velocity versus time, and acceleration versus time, to get a feel for what we're doing graphically as well as computationally. So here's time and acceleration rate. So we had the velocity versus time graph, which is a cubic, so it looks something like this. And what we're trying to find is at 2 seconds, let's say here, what is the acceleration rate? So graphically, what we're trying to find is, if I go to that point, we're trying to find the slope of the line at that point. So we need to go to the next graph down and take a derivative. Later videos will go up a graph and integrate so we can find changes in position. So step one, the equation is A is equal to dv dt. It's the derivative of velocity with respect to time. Okay. Step two, the variables. So the variables we have are what? Let's see. Velocity as a function of time we know. So that's 2t cubed meters per second. And the acceleration rate we do not know. So acceleration as a function of time is, I don't know. Okay. Which we're trying to solve for. In step three, solve. Let's see, we're breaking it up in a three-step process. Let's see. A, we'll say A is equal to dv dt, which in our case is equal to ddt of 2t cubed. Okay. B, we'll say, we'll actually differentiate, so this is going to be equal to the derivative. So this is relatively simple, so it's going to be equal to 6t squared meters per second squared, and then finally we're going to say evaluate it at 2 seconds. So let's see, at 2 seconds we're going to get 6 times 2 quantity squared, which is equal to a grand total of 24 meters per second squared. So that's the acceleration rate at that point. Box your answer. And we can say in the I direction because it's turning to the right, I direction. So what we just did is this. We found the equation for the acceleration versus time, which is a 6t squared by taking a derivative. So this is 6t squared. And so at 2 seconds, right here, 2 seconds, what we're saying is that that value of 2 seconds, the acceleration rate is 24 meters per second squared. And so once we have this equation, 6t squared, we can find the acceleration at any time. Let's say at 1 second, halfway through here, let's say, we can find out what that acceleration rate is. So for differential calc problems with derivatives, we're going to sketch some mini graphs. Here are position, velocity, and time. We may have different graphs depending on the problem. We may have force versus time, or force versus distance, or what have you. Then then state the derivative that you're going to use, the variables, and then three-step process. Show the work that you're going to do, take a derivative, and evaluate at a given point. So that's the setup for a derivative type problem.